What if you could travel through time? Think about that for just a moment, really think about it. Would you journey into the past to witness history unfold with your own eyes? Or would you leap forward into the future to see what wonders and challenges await humanity? It's one of the most captivating questions we can ask ourselves, a thought experiment that has fascinated scientists, storytellers, and dreamers for centuries. Time travel isn't just a staple of science fiction anymore. It's a serious subject of scientific inquiry, a playground for philosophers, and a source of endless wonder for anyone who's ever looked up at the stars and wondered what might be possible. Welcome, everyone. Today, we're embarking on a journey through 30 of the most mind-bending theories about time travel. Ideas that challenge not only what we think we know about the universe, but the very nature of reality itself. From Einstein's theory of relativity to quantum mechanics, from paradoxes that twist logic into knots to philosophical concepts that question the flow of time, we're going to explore it all. This isn't just a list of abstract ideas, it's an invitation to imagine, to question, and to see the cosmos in a whole new light. So get comfortable and open your mind, because we're about to dive into a topic that stretches the limits of imagination. Whether you're a science enthusiast, a curious thinker, or someone who simply loves a good mystery, there's something here for you. We'll uncover theories that are grounded in real physics and others that venture into the wonderfully speculative, each one offering a unique perspective on one of humanity's oldest and most thrilling dreams. The adventure starts now. Our first stop on this incredible journey brings us face to face with the most famous time travel conundrum of all, the grandfather paradox. Picture this scenario: you build a time machine, travel back to a time before your parents were born, and somehow prevent your own grandfather from meeting your grandmother. Without that meeting, your parent is never born, and consequently, neither are you. But if you were never born, how could you have traveled back in time to alter those events in the first place? This is the paradox in its purest form, a logical puzzle that seems to tie itself into an impossible knot, challenging the very feasibility of backwards time travel. Physicists and philosophers have proposed several fascinating resolutions to this paradox. One prominent idea is the Novikov self-consistency principle, proposed by Russian physicist Igor Novikov. This principle suggests that the timeline is essentially immutable. Any actions taken by a time traveler were always a part of history. In this view, you might travel to the past with the intention of changing something, but your actions would only end up ensuring that history unfolds exactly as it always did. You couldn't actually change the past because you already did what you always did. It's a concept that preserves causality but completely eliminates free will in the context of time travel. Another compelling solution comes from the many worlds interpretation of quantum mechanics. This theory posits that with every decision or random event, the universe splits into multiple branches, creating a vast multiverse of parallel realities. Under this model, if you travel back and prevent your grandfather from meeting your grandmother, you wouldn't be erasing your own existence in your original timeline. Instead, you'd simply be creating a new, divergent branch of reality where you were never born, while your original timeline remains completely untouched. You'd be a stranger in a strange new world, a living paradox from a universe that continues on without you. This paradox has also been a fantastic engine for science fiction storytelling, providing the central tension for countless books, movies, and TV shows. In the iconic film Back to the Future, Marty McFly nearly erases his own existence by accidentally interfering with his parents' first meeting, a plot that perfectly visualizes the stakes of the grandfather paradox for a mass audience. Other stories, like The Time Machine or episodes of Doctor Who, often play with these rules, exploring the terrifying or tragic consequences of meddling with established events. It's a narrative device that forces characters and us, the audience, to confront profound questions about destiny, responsibility, and the interconnectedness of all events. If the grandfather paradox leaves you wondering about the feasibility of changing the past, the bootstrap paradox might just convince you that the past was never as solid as we thought. Also known as an ontological paradox, this mind-bender concerns things, whether physical objects or pure information, that seem to have no point of origin. They simply exist in a closed, endless loop with no creator and no beginning. Think of a time traveler who is a huge fan of Shakespeare. He travels back to Elizabethan England, manuscript in hand, hoping to get the bard's autograph. But he accidentally drops his complete works of Shakespeare, which are then found by a young William himself. The aspiring playwright simply copies the plays and passes them off as his own, becoming the legendary figure we know. So, who actually wrote Hamlet? The plays were never created, they were just always there, trapped in an infinite cycle with no true author. This is the essence of a causal loop. An event in the future becomes the cause of an event in the past, which itself is the cause of that future event. It's a circle of cause and effect with no starting point, a loop that seems to defy the fundamental logic that everything must have a beginning. Unlike the grandfather paradox, which presents a contradiction that seems to break time, the bootstrap paradox presents a consistent loop. There is no logical inconsistency, the timeline is stable. The paradox isn't in a contradiction, but in the profound philosophical headache it induces about origin and creation. It challenges the very idea that anything can be truly invented, only discovered, or perhaps rediscovered from a future that already contains it. We can even find strange analogies to this in the real world of physics. Consider the behavior of certain subatomic particles. In some interpretations of quantum mechanics, a particle can be influenced by an event in its future, blurring the hard line between cause and effect. While not a perfect mirror of a time traveler giving Shakespeare his own work, it hints that at the most fundamental levels of reality, our classical understanding of a straightforward, linear progression of time might be incomplete. The universe itself might not be as strict about what comes first as we are. This paradox forces us to question the nature of information itself. Is information ever truly created, or is it a fundamental property of the universe, simply waiting to be found and arranged? If a symphony, a mathematical formula, or a technological blueprint can be bootstrapped into existence, it suggests that all ideas might exist in a kind of Platonic realm, independent of human minds. A time traveler wouldn't be bringing something new into the past, they would just be the mechanism that places it into its own timeless loop. It's a concept that diminishes the role of the inventor and elevates the role of the discoverer in a truly cosmic sense. But if the idea of a single, unchangeable timeline or a closed causal loop feels too restrictive, then the next theory might be the liberating answer you've been searching for. This brings us to Hugh Everett's groundbreaking many worlds interpretation of quantum mechanics, a theory that doesn't just resolve time travel paradoxes, it completely redefines our understanding of reality itself. Everett proposed that every single time a quantum event occurs with multiple possible outcomes, the universe doesn't just choose one. Instead, it splits, branching off into a new, parallel reality for every single possibility. Every flip of a coin, every decision you make, every random subatomic decay creates a new universe where the other outcome happened. The result is a constantly expanding, infinite multiverse where everything that can happen does happen in some branch of reality. This has a profound and elegant implication for time travel. Under the many worlds interpretation, the grandfather paradox simply ceases to be a paradox. If you were to travel back in time and prevent your grandfather from meeting your grandmother, you wouldn't be altering your own past. Instead, the moment you arrive in the past or the moment you take that life-altering action, you cause a new branch to split off from the timeline you remember. In this new, separate universe, you were never born. but your original universe, the one you left behind, remains completely untouched and unchanged. You haven't erased yourself, you've merely become a visitor in a new reality where your own personal history never unfolded. This means time travel could be possible without any logical contradictions, because you're not rewriting history, you're just hopping between the infinite pages of a cosmic history book. This concept of infinite realities opens up staggering questions about identity, free will, and our place in the cosmos. If every choice spawns a new universe, are we truly making decisions, or are we just experiencing one predetermined path out of an infinite number? Is there a version of you who became an astronaut, another who never left their hometown, and another who is reading this script back to you from a parallel YouTube channel? The many worlds interpretation suggests that all these versions are equally real, living out their lives in their own separate universes. It's a humbling thought that diminishes our central role in the cosmos while simultaneously affirming that every possibility for our lives is, in a sense, being realized somewhere. This mind-bending theory has captured the imagination of popular culture, providing the foundation for some of the most creative storytelling we've seen. The brilliant film Everything Everywhere All at Once is a perfect example, visualizing the emotional and existential weight of tapping into the skills and memories of your infinite other selves. It's not just about martial arts or hot dog fingers. It's about the profound loneliness and connection that comes from knowing every path not taken is a life being lived by another you. Other stories from Philip K. Dick's novels to the Marvel Cinematic Universe explore the drama and conflict that arises when these parallel worlds collide. They use the science as a springboard to explore very human questions about regret, destiny, and the choices that define us. While still a subject of intense debate among physicists, the many worlds interpretation offers a powerful and paradox-free framework for imagining time travel. It transforms the time traveler from a potential destroyer of history into an explorer of realities, forever stepping into new worlds shaped by every possible event. It suggests that the cosmos is far grander and more complex than we could ever perceive from our single, narrow vantage point. But if navigating infinite parallel realities seems complex, the next theory brings us back to the solid, yet still astonishing, predictions of Einstein's own equations. General relativity tells us that mass and energy warp the fabric of spacetime itself, creating what we experience as gravity. And within this warped geometry, the math allows for something truly extraordinary: closed time-like curves. A time-like curve is simply the path an object takes through the four-dimensional universe. It's your own personal world line from birth to this very moment. A closed time-like curve is a path that loops back on itself, allowing an object or a person to return to their own past without ever exceeding the speed of light. It's a theoretical road through the cosmos that forms a complete circle in time, a bridge engineered not by magic but by the severe and beautiful rules of physics. The mathematical foundation for this lies in solutions to Einstein's field equations that describe universes with very specific and very extreme conditions. One of the most famous examples is the Gödel universe, a solution found by the brilliant logician Kurt Gödel. This model describes a rotating universe where the centrifugal force of the entire cosmos spinning creates these closed loops in time. While our universe doesn't appear to match Gödel's model, it proved a vital point: closed time-like curves are not science fiction. They are a mathematically valid possibility within the framework of our best theory of gravity. This opened the door for physicists to explore other, more plausible cosmic structures that could host these time loops. Two of the most discussed structures are wormholes and rotating black holes. A wormhole, or Einstein-Rosen bridge, is a hypothetical shortcut connecting two distant points in spacetime. Physicist Kip Thorne and his colleagues famously calculated that if you could somehow stabilize a wormhole, using a hypothetical form of matter with negative energy, you could then manipulate its two mouths. If you took one mouth and accelerated it to a significant fraction of light speed and then brought it back, time dilation from special relativity would cause that end to have aged less than the stationary end. Connecting these two mouths would then create a time machine. Walking through in one direction would send you to the past, while walking through the other would send you to the future. The wormhole itself becomes a physical embodiment of a closed time-like curve. Similarly, the immense gravitational fields around rotating black holes, described by the Kerr solution to Einstein's equations, could also permit these paths. The dizzying spin of a Kerr black hole drags spacetime around with it, an effect known as frame dragging, potentially twisting it into a torus or donut shape just outside the event horizon. Within this region, called the ergosphere, the fabric of spacetime is so warped that the future light cone, which defines all possible paths into the future, tips over until it points into the past. An object navigating this chaotic region could, in theory, find a stable orbit that is also a loop in time, endlessly cycling through its own history. So why do respected theorists like Kip Thorne entertain these ideas if they sound so much like fantasy? It's because the math checks out. The equations of general relativity do not explicitly forbid these curves, they present them as solutions. This forces physicists to take them seriously as a theoretical possibility, a feature of the universe's operating system that, under the right conditions, could be activated. Thorne himself approached it with a scientist's curiosity. If the laws of physics don't say no, then we must ask how. And in asking that question, we often discover profound new truths about those very laws. The study of closed time-like curves has led to deeper insights into quantum gravity, the nature of causality, and the fundamental structure of the universe, proving that even seemingly outlandish thought experiments have immense value. They are the ultimate stress test for our physical theories. Yet for all the theoretical elegance of wormholes and black holes, they present a monumental practical challenge. They require truly astronomical amounts of energy and conditions we can barely conceive of, let alone create. But what if there was another path, a set of ready-made cosmic structures that could be repurposed into a time machine? This brings us to one of the most exotic and fascinating concepts in all of theoretical cosmology, the idea of using cosmic strings. Imagine the very earliest moments after the Big Bang, when the universe was a seething, unimaginably hot and dense soup of energy and forces. As it expanded and cooled, physicists believe it may have undergone a series of phase transitions, much like water freezing into ice. And just as ice crystals can form with cracks and imperfections, these cosmic phase transitions might have left behind defects, one-dimensional cracks in spacetime known as cosmic strings. These aren't strings in the everyday sense. A cosmic string is a hypothetical object, an infinitely long, unimaginably thin filament of pure energy, thinner than a proton but with the mass of a mountain range packed into every inch of its length. This immense density gives it a gravitational pull so intense that it warps the spacetime around it in an extremely peculiar way. The geometry around a straight cosmic string is not like the curved space around a planet or star. Instead, it's a flat plane that has simply had a narrow wedge removed, like a pie with one slice missing. If you were to travel in a perfect circle around a cosmic string, you would find that your total journey is less than 360 degrees. This bizarre geometry has a direct and incredible consequence for time travel. The real magic happens not with one string, but with two. Picture a pair of these infinitely long, ultra-dense cosmic filaments moving past each other at a significant fraction of the speed of light. The combined gravitational field of these two moving strings would twist the fabric of spacetime so severely that it could form a closed time-like curve. A spacecraft could, in theory, navigate a precise figure-8 path around these two passing strings and find itself not just in a different location but in its own past. Unlike the wormhole time machine, which requires exotic matter to hold it open, This method relies solely on the known physics of gravity and the mind-bending geometry these primordial defects create. It's a time machine built from the leftover scaffolding of the universe itself. The challenge, of course, is that cosmic strings remain entirely hypothetical. We have no confirmed observational evidence that they actually exist. They are predicted by some grand unified theories which attempt to merge the fundamental forces of nature, but their existence is far from certain. If they do exist, they would be incredibly difficult to detect. They might reveal themselves through their dramatic gravitational lensing effects, warping the light from distant galaxies into double images, or by creating faint ripples in the cosmic microwave background, the afterglow of the Big Bang. Astronomers have searched for these signatures, but so far the hunt has come up empty. Even if we were to find one, the engineering required to use it as a time machine is beyond anything we can currently imagine. We would need to locate not just one, but two of these objects, and then figure out how to maneuver them or ourselves with a precision that dwarfs all of human technological achievement. Yet, the sheer possibility is what captivates physicists. The concept of cosmic string time machines shows that the universe might have built time travel capabilities into its very fabric from the very beginning, not as a bug, but as a feature waiting to be discovered in the deep geometry of reality. It turns the cosmos from a static stage into a dynamic, intricate machine with hidden functions we are only just beginning to decode. While cosmic strings rely on hypothetical remnants from the Big Bang, another proposal for a time machine is something we could, in theory, build ourselves if we had access to truly godlike technology. This brings us to Tipler's cylinder, a concept put forward by physicist Frank Tipler in 1974. Imagine constructing a cylinder with a mass roughly equivalent to our entire Sun, but compressed into a structure that is infinitely long and incredibly dense. Now, set this impossibly massive object spinning on its axis at a significant fraction of the speed of light, perhaps over half the speed of light. According to Tipler's calculations, the sheer mass and dizzying rotation of this cylinder would warp the fabric of spacetime around it so severely that it would literally drag spacetime along for the ride, a phenomenon known as frame dragging. This creates a vortex around the cylinder where the paths through spacetime, the time-like curves we discussed earlier, are twisted into closed loops. A spacecraft following a precise spiral orbit around this spinning cylinder could find itself following one of these loops, traveling back to a point in its own past. The mathematical elegance of Tipler's idea is that it stays entirely within the proven framework of general relativity. It doesn't require any hypothetical exotic matter or undiscovered cosmic phenomena. It just requires an almost unimaginable amount of perfectly normal matter and an equally staggering amount of energy to set it spinning. The equations show that if you could somehow meet these extreme conditions, the cylinder would create a region of space around it where time is twisted into a circle, forming a closed time-like curve and making travel into the past a genuine possibility. It's a solution that is, on paper, perfectly valid according to Einstein's theory. However, the practical hurdles instantly reveal why this remains a thought experiment. The first and most obvious problem is the requirement for the cylinder to be infinitely long. In our finite universe, we simply cannot construct an object of infinite length. Tipler himself suggested that a very long but finite cylinder might still work, but later calculations by other physicists showed that a finite cylinder would not produce the same stable, consistent closed time-like curves. It would likely lead to chaotic and unstable regions of spacetime, making controlled time travel impossible. The second, equally monumental challenge is the material strength required. A cylinder with the mass of a sun, spinning at relativistic speeds, would be torn apart by immense centrifugal forces long before it reached the necessary rotational velocity. No known or theorized material could withstand such incredible stresses. It would instantly collapse into a black hole under its own gravity long before it could ever function as a time machine. For these reasons, most physicists view Tipler's cylinder as a fascinating mathematical curiosity rather than a plausible blueprint for a real device. It serves a more important purpose as a kind of stress test for general relativity, helping us understand the limits of the theory and the extreme conditions under which its predictions might break down or lead to paradoxical situations. It stands as a testament to the sheer weirdness hidden within Einstein's equations, showing us that the universe allows for possibilities that are simultaneously mathematically sound and physically unachievable, a reminder that the map of reality is not the territory itself. While constructing an infinite cylinder of stellar mass is a feat of engineering beyond our wildest dreams, another theoretical time machine emerges from the equations of general relativity that feels slightly more tangible, if no less fantastical: the traversable wormhole. Often depicted in science fiction as a shimmering tunnel through the stars, a wormhole is fundamentally a shortcut. Einstein's theory tells us that massive objects like stars and planets warp the fabric of spacetime, creating the dimples and curves we experience as gravity. A wormhole takes this a step further, theorizing a bridge, a literal tunnel, that connects two distant points in spacetime, folding the universe so that a journey that might take billions of years at light speed could instead be a quick stroll through a cosmic doorway. The incredible potential of a wormhole isn't just for crossing vast distances in space, it's for crossing vast distances in time. This idea was popularized and rigorously explored by the renowned physicist Kip Thorne and his colleagues, who were inspired by a question from Carl Sagan for his novel Contact. To function as a time machine, you would need a stable, traversable wormhole. Imagine you have such a tunnel with two mouths, let's call them mouth A and mouth B. You leave mouth A here on Earth, and then you take mouth B on a journey. You accelerate it to a significant fraction of the speed of light and bring it back. Due to the effects of time dilation from Einstein's special relativity, time would pass more slowly for the traveling mouth. While 10 years might pass on Earth at mouth A, only 1 year might pass for the roving mouth B. Now, the wormhole is a tunnel that connects these 2 points that are no longer just separate in space, but also 9 years apart in time. If you were to step into mouth A in the year 2040, you would instantly exit from mouth B into the year 2031. You've traveled 9 years into the past, step back through from mouth B, and you'd return to your future at mouth A. This creates a stable, two-way time machine, a closed time-like curve made not from cosmic strings but from a manipulated tunnel in the fabric of reality. However, there's a monumental catch keeping this incredible idea in the realm of theory: the wormhole's stability. The equations of general relativity show that any wormhole would be incredibly unstable. The moment it formed, it would likely collapse into a singularity faster than light, or even a single photon could pass through it. To prevent this catastrophic pinch-off and make the wormhole traversable, you would need a very special kind of ingredient to line its throat: exotic matter. This isn't just matter from another planet, it's matter with a negative energy density, possessing what's called a negative average null energy condition. In simpler terms, this exotic matter would have repulsive gravity, actively pushing spacetime apart rather than pulling it together. It would act as a counterforce to gravity, propping the wormhole's throat open wide enough for something to pass through. While certain quantum effects, like the Casimir effect, show that tiny amounts of negative energy density can exist in a lab, the quantities needed to stabilize a macroscopic wormhole are astronomical and far beyond anything we can produce or even confirm is possible. The search for, or the creation of, this exotic matter is the single greatest barrier to making a wormhole time machine a reality. Despite the daunting physics, the conceptual elegance of the wormhole time machine has cemented its place as a cornerstone of both scientific thought and iconic storytelling. In literature and film, it provides a wonderfully visual and narratively flexible mechanism for time travel. The aforementioned Contact, both the novel and the film, uses a wormhole transportation system built by an advanced alien civilization to send Dr. Ellie Arroway across the galaxy. The movie Interstellar features a meticulously designed wormhole near Saturn, which serves as a gateway to distant star systems and ultimately to a deeper manipulation of time itself through a higher dimensional tesseract. These stories borrow from the real science to ground their fantastic journeys, introducing audiences to concepts like time dilation and spacetime geometry in a powerful and memorable way. The wormhole's appeal lies in its promise of two-way travel. Unlike some theories where you might be stranded in the past or create a new branch universe, the wormhole offers a connection, a door you can walk through and then walk back through again. It suggests the possibility of not just being a tourist in time, but a commuter. You could potentially observe historical events, return to your present, and then go back to check your notes, all while maintaining a consistent and paradox-free timeline, depending on which model of time you subscribe to. It transforms time from a river we can only float down into a landscape we might one day learn to navigate. But if manipulating the fabric of space-time with massive objects feels like engineering on a cosmic scale, then the next theory brings our quest for time travel down to the smallest, most fundamental level of reality. Welcome to the bizarre and counterintuitive world of quantum time travel. At the quantum scale, the rules are very different from the ones we experience in our everyday lives. Particles can be in two places at once. They can be spookily connected across vast distances, and as we're about to see, they might even be able to send information backwards in time. This isn't about building a chrome-plated machine. It's about harnessing the innate weirdness of the quantum realm. One of the most startling proposals in this area is the concept of quantum teleportation into the past. You might have heard of quantum teleportation, a very real process where the quantum state of a particle, its unique identity card, is instantly transmitted from one location to another using a phenomenon called quantum entanglement. But some physicists like Seth Lloyd have proposed a dazzling twist on this idea. His theory suggests that by carefully manipulating entangled particles, it might be possible to teleport a quantum state not just through space but backwards through time. Imagine you have a particle here and now. Through a complex series of quantum operations involving its entangled partner, you could, in theory, change the state of that particle in the past. It's as if you could send a message to yesterday, instructing a particle to be in a different position than it was, all without any classical signal ever traveling backwards. This doesn't violate causality in the usual sense because no information is being sent back in a way that could create a paradox. It's more like the universe is performing a global calculation where the outcome in the present seamlessly updates the initial conditions in the past to maintain consistency. This leads us to an even more mind-bending idea: post-selection. In standard quantum mechanics, we say a particle exists in a superposition of all possible states until we measure it, forcing it to choose one outcome. Post-selection is like conducting an experiment in reverse. Instead of setting up an initial state and seeing what happens, you specify the outcome you want to see at the end of the experiment, and then work backwards to figure out what the initial conditions must have been to guarantee that result. In the context of time travel, this is the quantum equivalent of saying, I want to arrive safely in the past, and the laws of physics would then naturally ensure that all your actions in the past were consistent with that safe arrival, effectively preventing any paradoxes before they could even occur. It's a way of hand-picking a self-consistent timeline from the infinite multitude of possibilities offered by the quantum world. The most famous experiment suggesting this quantum retrocausality is the quantum delayed choice experiment, a brilliant extension of John Wheeler's original thought experiment. In one stunning implementation, scientists sent photons towards a beam splitter, which can either act as a mirror to send them on one path or as a gateway that lets them take two paths at once, creating an interference pattern. The incredible twist is that the decision of whether to measure the photon as a particle on one path or as a wave taking both paths was made after the photon had already passed through the beam splitter, but before it was detected. Astonishingly, the measurement choice in the present seemed to dictate how the photon had behaved in the past. It's as if the photon knew retroactively whether it needed to have been a particle or a wave. This isn't proof positive of time travel, but it dramatically challenges our classical, common-sense notion of a rigid temporal sequence where cause must always precede effect. At the quantum level, the universe might not care about our arrow of time. These experiments force us to confront a radical possibility that the quantum world is fundamentally a causal. The future might not just be influenced by the past, the influence might flow both ways, with future events reaching back to tweak the present and the past. This doesn't mean you could go back and prevent your own birth. The universe seems to have safeguards against such glaring paradoxes, perhaps through the mechanism of post-selection, ensuring only consistent histories play out. But it does suggest that time itself might be an emergent property, a large-scale illusion that arises from the collective behavior of quantum particles. When we look closely enough, the smooth, flowing river of time breaks down into a foaming, bubbling quantum sea where temporal order is fluid and malleable. This perspective doesn't just offer a new mechanism for time travel, it fundamentally redefines what time actually is. But if the quantum world suggests a fluid and interactive relationship with time, a very different and equally compelling solution to the paradox problem comes from the world of cosmology. This brings us to the Novikov self-consistency principle, a bold and elegant proposal from Russian physicist Igor Novikov. He tackled the grandfather paradox head-on with a simple yet profound assertion: the timeline of the universe is immutable. Any actions taken by a time traveler were always a part of history. In this view, you cannot change the past because you already did what you always did. Your journey back and all your actions there are fixed events, woven into the immutable fabric of space-time from the very beginning. The universe, according to Novikov, possesses a kind of built-in cosmic censorship that prevents logical inconsistencies from ever occurring. If you traveled to the past, you were always there. Your attempt to prevent your grandfather's meeting would inevitably fail. Your gun would jam, you'd get lost on the way, or you'd discover you were the very reason they met in the first place. The principle enforces a single, consistent, and predetermined timeline where free will, at least when it comes to altering past events, is nothing but an illusion. This idea has deep and somewhat unsettling implications for our understanding of choice and destiny. If Novikov is correct, then the entire history of the universe, from the Big Bang to the present and beyond, is a single, unchangeable story. Every event, every decision, and every time travel journey is a fixed paragraph in that story. You might feel like you are making choices, but any choice you make that could alter the timeline is simply impossible. Your path is set. This resonates with philosophical concepts of fatalism and determinism, suggesting that we are all merely acting out a script that has already been written. The appeal of this principle for physicists is its sheer simplicity and its powerful resolution of the most frustrating time travel paradoxes. It doesn't require multiple universes or complex quantum mechanics. It just requires that the universe is consistent with itself, a notion that feels almost axiomatic. We can see the Novikov principle brilliantly illustrated in popular culture, and one of the cleanest examples comes from J.K. Rowling's Harry Potter and the Prisoner of Azkaban. Throughout the book, Harry believes he is being saved by his deceased father, only to discover in the climax that he and Hermione have traveled back in time. The events they witness, the rock thrown through the window, the Patronus charm that saves their past selves, were not caused by some mysterious third party. They were caused by their own future actions. They were always there, fulfilling the role they thought belonged to another. They didn't change the past, they completed it. Their actions were a vital, self-consistent part of the history that had already unfolded. The story presents a perfect, paradox-free loop where the cause is the effect and the effect is the cause, all seamlessly locked together. It's a narrative embodiment of Novikov's idea, showing us a universe that politely refuses to allow contradictions. This principle doesn't mean time travel would be boring or without stakes. The drama simply shifts. The tension is no longer about whether you can change the past, but about the shocking discovery of what your role in it always was. The horror isn't in accidentally preventing your own birth. It's in the realization that you were always the villain or the tragic figure destined to cause the very event you traveled back to prevent. You are not an author rewriting history, but an actor discovering your lines for the first time, even though they were written eons ago. It transforms the time traveler from an active force of change into a passive agent of fate, forever bound to play their part in a cosmic play where the script is already complete. While the Novikov principle presents a universe of fixed fate, Einstein's theory of relativity offers us a form of time travel that is not only possible but regularly verified by modern technology. This is the incredible reality of time dilation, a direct consequence of the fact that time is not a universal constant ticking away at the same rate for everyone. Instead, Einstein revealed that time is elastic, stretching and compressing based on two key factors, velocity and gravity. The faster you move through space, the slower you move through time relative to someone who is stationary. Similarly, the stronger the gravitational field you're in, the more time slows down for you compared to someone in a weaker field. This isn't science fiction. It's a fundamental property of our universe, and it provides us with a one-way ticket to the future. The most famous illustration of this is the twin paradox. Imagine a pair of identical twins. One remains here on Earth, while the other boards a spacecraft capable of traveling at an enormous fraction of the speed of light, say 90%. The traveling twin journeys to a distant star and back. For the twin on the rocket, the trip might only take, from their perspective, 10 years. But due to the effects of time dilation, upon returning to Earth, they would step out of their ship to find that their Earth-bound sibling has aged 20 years or more. The spacefaring twin has effectively traveled 10 years into the Earth's future. They haven't experienced any mystical journey. They have simply been moving through time at a different rate than everyone else on our planet. Their clock, their heartbeat, their biological aging, all of it was slowed down by their incredible velocity. This effect is not just theoretical. We measure it every single day with the Global Positioning System. Each GPS satellite orbits the Earth at high speed, and just as importantly, at a higher altitude where Earth's gravity is slightly weaker. Both of these factors cause time on the satellites to pass at a different rate than it does on the ground. Special relativity tells us their speed makes their clocks run slower, while general relativity tells us the weaker gravity makes their clocks run faster. The net effect is that without constant, precise adjustments, the GPS system would accumulate errors of several miles per day, rendering it useless. Engineers must actively correct for these relativistic effects, proving that time dilation is a real, measurable phenomenon that we must account for to make our advanced technology work. We are, in a very real sense, already managing time travel in our daily lives. This form of time travel is profound in its accessibility and its limitation. It is a one-way journey. You can use velocity or gravity to jump forward into the future of your original reference point, but there is no known mechanism within relativity that allows you to turn around and come back. You cannot travel back to the present you left. You can only move forward into the new future you have arrived in. It also requires truly extreme conditions to create a noticeable effect. While the time difference for GPS satellites is measured in millionths of a second, to leap decades or centuries into the future would require sustaining velocities incredibly close to the speed of light or spending time near an immensely powerful gravitational source like a neutron star or a black hole. The energy requirements for such a feat are currently beyond our reach, but the physics itself is sound and undeniable. This establishes time dilation as the first and only proven form of time travel. It doesn't require wormholes, cosmic strings, or paradoxical loops. It requires only that we accept the universe as described by Einstein over a century ago, a four-dimensional fabric of spacetime where our experience of time is deeply personal and relative to our own state of motion. It means that every time we move or experience gravity, we are ever so slightly time travelers, sliding into the future at our own unique pace. For the adventurous, it opens up the tantalizing possibility that humanity could one day build ships capable of such fantastic journeys, sending explorers on missions that would return them to Earth centuries after they departed, becoming living relics of a bygone era they never experienced. If the concept of time dilation makes your head spin with its relative nature, then the block universe theory might just completely redefine your entire perception of reality. This theory, also known as eternalism, proposes a staggering idea. The past, present, and future are not sequentially replacing one another. Instead, they all exist simultaneously, frozen together in a single, four-dimensional structure, a vast and unchanging block of spacetime. In this view, your birth, you watching this video right now, and every moment of your future are all equally real. They are fixed locations within this immense block, much like different cities are fixed locations on a map. Time in this model doesn't flow in the way we feel it does, it just is. We are simply conscious observers moving along our personal world line, experiencing one slice of the block at a time in a rigid order, which creates our powerful yet possibly illusory sensation of a flowing present. This idea finds a strong foundation in Einstein's own theory of relativity, which fused space and time into a single entity, spacetime. A key insight from relativity is that there is no universal now. What is the present moment for you depends entirely on your frame of reference and your state of motion. An event that is in the future for one observer could be in the past for another. The block universe is the natural interpretation of this reality. It takes all these different, equally valid perspectives and says that if no single now is privileged, then all moments must be equally real. The entire timeline, from the Big Bang to the ultimate fate of the cosmos, is laid out in this single, static structure. Your life is not a burning fuse. It is more like a completed film strip, with every frame from beginning to end existing eternally. This has a profound and direct implication for time travel. If the block universe is real, then the past and future are not realms that have ceased to exist or have not yet come into being. They are simply other places. In the same way that you can travel from New York to Paris, a time traveler would, in theory, just need a vehicle capable of moving through the fourth dimension time to visit the year 1920 or the year 3000. There would be no paradox in arriving at a different temporal coordinate because you're not changing anything. You are just journeying to a different part of the unchanging block. Your arrival in the past was always a part of that past history, neatly written into the fabric of the universe. The block universe theory is in many ways the perfect philosophical partner to the Novikov self-consistency principle, providing a physical model for a timeline where everything is predetermined and paradoxes are a logical impossibility. Yet, this view stands in stark contrast to our most fundamental human experience. We feel, with every fiber of our being, that the present is special and that the future is open and unwritten. This opposing view is called presentism, the belief that only the present moment is real. The block universe can feel deeply impersonal and even fatalistic. If everything is already written, what becomes of free will? Are our choices and struggles merely illusions, just us reading lines from a cosmic script we cannot see? Some philosophers and scientists argue that our conscious experience of a flowing present is the primary reality, and that the block universe, while mathematically elegant, is a cold abstraction that fails to account for the qualitative feel of being alive and making decisions. Despite this philosophical tension, the block universe remains a compelling framework for many physicists because it so neatly avoids the messy paradoxes of other time travel models. It suggests that the universe is a single, coherent, and self-consistent object. Traveling to the past isn't about rewriting history, it's about visiting a location that has always contained your arrival. You are always going to be there. This perspective transforms the time traveler from an agent of chaos into a tourist of eternity, simply hopping between points in a reality that is complete and whole. It invites us to see our lives not as fleeting sparks, but as timeless sculptures within an infinite cosmic gallery, forever fixed in the grand design of spacetime. While the block universe presents a grand, static vision of all time, another revolutionary concept emerges from the quantum realm that suggests time itself might have a more dynamic and structured nature. This brings us to one of the most fascinating and recent developments in theoretical physics, the discovery of time crystals. First proposed by Nobel laureate Frank Wilczek in 2012, a time crystal isn't a glittering mineral from a science fiction story. It's a proposed new phase of matter, a structure that has movement and rhythm built into its very fundamental state. To understand how extraordinary this is, we first need to consider an ordinary crystal, like a diamond or a snowflake. These are spatial crystals. Their atoms are arranged in a repeating, periodic pattern in space. A time crystal does something analogous, but in the dimension of time. Its structure repeats not from one point in space to another, but from one moment in time to the next, oscillating in a predictable, periodic cycle. The most mind-bending property of a time crystal is that this oscillation theoretically occurs in its ground state, the lowest energy state possible. In the everyday world, anything that moves or oscillates loses energy to friction and eventually stops. A pendulum swings back and forth because you gave it a push, imparting energy, and it will gradually slow down. A time crystal, however, would continue its rhythmic motion indefinitely without any energy input. This sounds suspiciously like the fabled perpetual motion machine, but it's crucially different. A perpetual motion machine of the first kind would create energy from nothing, violating the conservation of energy. A time crystal doesn't create energy. It doesn't output any energy at all. It's a system that is already in its lowest energy state, yet it is perpetually in motion, a concept that seems to defy our classical intuition but is permitted by the strange rules of quantum mechanics. This unique behavior is tied to a profound concept in physics known as symmetry breaking. The laws of physics are generally symmetric under translations of time. They work the same way today as they did yesterday and as they will tomorrow. This is called time translation symmetry. A time crystal spontaneously breaks this symmetry. Even though the underlying laws are symmetric, the time crystal's ground state is not. It chooses a specific rhythm, a particular tick-tock, thus breaking the continuous symmetry of time into a discrete periodic pattern. It's as if time itself develops a kind of crystalline structure within this object. The creation of the first time crystals in the lab was a monumental achievement. Researchers at the University of Maryland and Harvard University, led by Christopher Monroe and Mikhail Lukin respectively, used chains of ytterbium atoms or nitrogen vacancy centers in diamond, precisely manipulated with laser pulses to create systems that exhibited this telltale periodic motion in their ground state, confirming Wilczek's radical hypothesis. So what does this have to do with time travel? The connection is speculative but thrilling. If a time crystal's oscillation is truly a break in the symmetry of time, it suggests that time might not be the smooth, featureless continuum we often imagine. Perhaps it has a grain to it, a fundamental periodicity or structure that could, in theory, be manipulated. Some researchers speculate that studying time crystals could lead to a deeper understanding of time's arrow, why we remember the past but not the future. Furthermore, the fact that these systems can maintain a form of perpetual, coherent quantum motion makes them a prime candidate for building incredibly stable quantum clocks or even components for quantum computers. In a far future scenario, one could imagine a technology that doesn't just move through time, but somehow locks onto or synchronizes with this fundamental temporal rhythm, using it as a reference frame or a stable anchor point for temporal navigation. While we are light years away from such an application, the very existence of time crystals proves that our understanding of time is still evolving, showing us that even in its lowest energy state, the universe is never truly still. Now, let's shift our focus from the cutting edge of physics to a theory that emerges from the shadows of history itself. This next idea is perhaps one of the most audacious and controversial on our list, suggesting that a fundamental error, or perhaps a grand conspiracy, has warped our entire perception of the past. Welcome to the phantom time hypothesis, a theory proposing that almost 300 years of history never actually happened. The concept was first put forward by the German historian Herbert Illig in the 1990s. He proposed that the years 614 through 911 Anno Domini were entirely fabricated, inserted into the historical record by a deliberate act of deception. According to this idea, we are not actually living in the 21st century. Instead, we are currently in the early 18th century. The three phantom centuries, the 7th, 8th, and most of the 9th, were invented, meaning events and figures we believe are from the years 900 or 800 actually occurred 297 years later. Illig's primary suspect for this massive chronological fraud was the Holy Roman Emperor Otto III and Pope Sylvester II. He theorized they conspired to change the calendar to place their reign at the symbolic millennial year 1000, thereby increasing their prestige and power by aligning themselves with a profoundly significant date in Christian eschatology. Proponents of this theory point to several key pieces of what they consider evidence. They argue there is a suspicious lack of reliable archaeological evidence from this period in Europe, suggesting a dark age that was dark because it simply didn't exist. They also highlight perceived anomalies in architectural styles, claiming that buildings like the Palatine Chapel in Aachen show no 297 years of architectural evolution from Roman styles, but instead appear to be a direct continuation. Another argument revolves around the adoption of the Gregorian calendar in 1582, which was implemented to correct a 10-day drift in the Julian calendar. Illig and his supporters calculated that the accumulated error since the First Council of Nicaea in 325 should have been 13 days, not 10. They claim this 3-day discrepancy is a ghost, a leftover clue pointing to the nearly 3 centuries of invented time that never contributed to the calendar's drift. However, this theory has been overwhelmingly and decisively debunked by historians, archaeologists, and scientists from a multitude of fields using evidence that is truly impossible to ignore. The most powerful refutation comes from the science of dendrochronology, or tree ring dating. Continuous tree ring chronologies have been established for thousands of years, using samples from ancient wood found in bogs, buildings, and archaeological sites across Europe and the world. These rings provide an unbroken annual record of climate conditions, and they match up perfectly across continents. There is no gap of 300 years in these records. The sequences from the 6th century connect seamlessly to those of the 10th century, providing an irrefutable natural clock that proves those years did in fact occur. Furthermore, the historical record is not nearly as empty as proponents claim. We have detailed chronicles from this period from cultures far beyond the reach of any supposed European conspiracy. The Byzantine Empire, the Islamic Caliphates, and China all have extensive, independent historical records that document events, rulers, and astronomical observations throughout these exact centuries. A conspiracy to erase 300 years would have had to somehow coordinate with and rewrite the entire history of the known world, an impossible feat long before modern communication. Crucially, astronomers can use ancient records of eclipses and other celestial events, which are precisely predictable backwards and forwards in time. Observations recorded in China, the Middle East, and Europe during the Phantom centuries align perfectly with astronomical calculations, offering yet another independent scientific verification that those years are real. So why does such a thoroughly debunked theory persist and continue to capture the public imagination? It taps into a powerful and seductive narrative, the idea that history is not what we are told, that hidden forces have manipulated our understanding of the world, and that a single, brilliant idea can overturn centuries of established knowledge. It's the ultimate conspiracy theory, one that doesn't just alter an event but rewrites the very timeline of human existence. It appeals to our desire to see ourselves as enlightened truth seekers, capable of seeing through a grand deception that has fooled everyone else. In a way, the phantom time hypothesis is a fascinating case study in how a compelling story can often feel more true than a complex, evidence-based reality, demonstrating that our fascination with time isn't just about physics, but about the very nature of truth and the stories we tell about our past. This brings us to a chilling and deeply philosophical twist on our journey, the predestination paradox. If the Novikov principle gave us the physics of a fixed timeline, the predestination paradox explores the crushing psychological and narrative weight of that inevitability. It describes a scenario where a time traveler's every effort to alter a past event inadvertently becomes the very cause of that event. Your actions don't change history, they cement it. You set out to prevent a tragedy, only to discover that your intervention was the essential ingredient that made the tragedy inevitable in the first place. It's a cosmic trap of the most cruel and ironic design, where free will is not just an illusion, but an active instrument of fate. We can trace the roots of this idea back to ancient storytelling, long before the concept of a time machine was ever invented. The classic tragedy of Oedipus Rex is arguably the oldest and most powerful example of a predestination paradox in narrative. An oracle prophesies that the infant Oedipus will one day kill his father and marry his mother. In a desperate attempt to avoid this horrific fate, his parents order him killed, but he is saved and raised by another family. Years later, hearing a similar prophecy, Oedipus flees his adoptive home to protect them, believing them to be his real parents. On the road, he gets into an argument and kills a stranger who, unknown to him, is his biological father, King Laius. He then solves the riddle of the Sphinx, wins the gratitude of Thebes, and is given the widowed queen Jocasta as his wife, his own mother. Every single step taken to avoid the prophecy directly led to its gruesome fulfillment. The characters had the illusion of choice, but their path was fixed, their actions preordained to bring about the very outcome they feared most. In modern time travel stories, this paradox creates a uniquely satisfying and often terrifying narrative structure. The brilliant film 12 Monkeys provides a masterclass in this. The protagonist, James Cole, is sent back from a plague-ravaged future to uncover the origin of the virus. His entire mission is driven by the belief that he can find and stop the army of the 12 monkeys, whom he believes released the pathogen. Yet his very presence in the past, his frantic actions, his cryptic warnings scrawled on walls, his interactions with the key suspects is what inspires and enables the mentally unstable Jeffrey Goins to form the 12 monkeys and set the plan in motion. Cole's journey doesn't prevent the apocalypse, it creates it. He is not a savior, he is the unwitting patient zero of the very idea he sought to destroy. The film's closing scene, where he as a child witnesses his own death in the past, perfectly seals this immutable loop. The psychological impact of this realization on a character is devastating. Imagine the horror of dedicating your life to a mission, risking everything, only to discover you were never the hero. You were the villain all along, or at the very least, fate's perfect pawn. This creates a profound sense of despair and futility, a feeling that the universe is not just indifferent, but actively malevolent in its design. It confronts us with the possibility that our deepest struggles and most determined efforts are meaningless in the grand scheme of a predetermined cosmos. Our sense of agency, which is so fundamental to our identity, is revealed to be a cruel joke, yet for the audience these stories can be incredibly satisfying. There is a deep, almost primal appeal to a perfectly closed loop, a narrative where every piece fits together with impeccable logic and no loose ends. The moment of revelation, when the character and the viewer understand how all the pieces connect, provides a powerful aha moment. It's the narrative equivalent of solving an elegant equation. The tragedy is not in the failure to change things, but in the tragic, beautiful inevitability of it all. This structure forces us to ask ourselves a difficult question. If you knew your every action was predetermined, would you still choose to be a good person? Would you still strive to do the right thing, even if you knew it was all part of a script? The predestination paradox doesn't just trap characters in time. It traps them in a philosophical dilemma about the nature of choice and meaning in a universe that may have already written every last word of our story. But if the predestination paradox traps us in a fixed and unchangeable timeline, a far more radical theory proposes a breathtaking escape. Perhaps the timeline itself is an illusion. This brings us to one of the most profound and mind-bending concepts in all of physics, the idea that time does not fundamentally exist. Think about that for a moment. Our entire lives are experienced as a sequence of moments, a relentless march from past to future. What if this is all a grand cognitive trick, a story our brains tell us to make sense of a universe that is, at its core, timeless? This isn't science fiction, it's a serious proposition from some of the most brilliant theoretical physicists working today. One of the leading voices in this field is Julian Barber, a physicist who has devoted his life to building a model of the universe without time. In Barber's view, the universe is not a movie, but a vast collection of still photographs. He calls each of these frozen snapshots a now. Every possible configuration of every particle in the universe, from the Big Bang to the heat death of everything, exists simultaneously in a static, infinite landscape he calls Platonia. In this timeless realm, there is no past and no future. There is only an endless, unchanging mosaic of nows. What we perceive as the flow of time, according to Barber, is simply our consciousness moving from one now to a very similar, adjacent now. Our sensation of duration and change is an emergent property, an illusion created by our brain's method of organizing these static frames into a coherent sequence. It's like a flip book. Each page is a static image, but when you thumb through them quickly, you see motion and a story unfolding. A similarly revolutionary perspective comes from the work of Carlo Rovelli, a founder of loop quantum gravity. Rovelli proposes a concept called relational time. He argues that time has no independent existence. It only arises from the relations and interactions between events. There is no universal clock ticking away in the background of the cosmos. Instead, time is a local phenomenon, a story we tell about how things change relative to each other. To understand this, imagine a universe with only two objects. You can only say that object A has moved relative to object B. Without a third object to use as a reference, the concept of a uniform, flowing time becomes meaningless. Time isn't a river we're all floating down. It's the current that emerges from the relationships between all the things in the water. At the most fundamental level, at the Planck scale, Rovelli suggests that this web of relations might even break down completely, revealing a reality where the very concepts of before and after cease to have any meaning. If these physicists are correct, the implications for time travel are not just challenging, they are utterly devastating. The entire enterprise of building a time machine becomes meaningless. You cannot travel to a past or a future that does not exist as a separate, accessible place. All moments, all nows are equally real and eternally present. A time traveler wouldn't be journeying through a fourth dimension. They would simply be shifting their conscious awareness from one point in the landscape of Platonia to another. The grandfather paradox evaporates because there is no linear chain of cause and effect to disrupt. Every now, including the one where your grandfather is a young man and the one where you are born, exists independently and permanently. The universe is a finished book, and we are simply reading it one word at a time, convinced the story is unfolding when, in fact, every chapter has already been written. You might be wondering how we could ever test such an abstract and non-intuitive idea. How do you run an experiment on the non-existence of time? Physicists are clever, and they are devising ways to look for the fingerprints of a timeless reality. One approach involves studying the very foundations of quantum mechanics and gravity. Some theories of quantum gravity suggest that at extremely small scales, spacetime becomes granular or foamy, losing its smooth, continuous nature. In this quantum foam, the standard ordering of events might break down. If experiments could detect this fundamental granularity or find evidence that the sequence of events can be reversed at the quantum level, it would lend serious credence to the idea that time is not fundamental. Another potential test comes from the study of entropy and the arrow of time. The fact that we remember the past and not the future is deeply tied to the second law of thermodynamics, which states that entropy or disorder always increases. But why was the entropy of the universe so incredibly low at the Big Bang? This is one of the deepest mysteries in physics. Timeless theories like Barber's might offer an answer. The Big Bang wasn't a beginning in time, but simply one particular now in the landscape of Platonia that happens to have a very low entropy configuration. From that point, the universe naturally evolves into higher entropy states, creating our local arrow of time. If models based on this concept can successfully predict other observable features of our cosmos, it would be a powerful argument in their favor. While we may not have a definitive experiment today, the very fact that scientists are designing ways to probe the nature of time shows that this is not mere philosophical speculation, but a cutting-edge frontier of physics. But if the timeless universe suggests a reality where every moment simply is, then perhaps the key to navigating it lies not in a physical machine, but within the confines of our own mind. This leads us to a profoundly different category of theories: consciousness-based time travel. Here, the vessel isn't a chrome-plated DeLorean or a swirling wormhole. It's the human consciousness itself, with the idea that through focused mental practices, chemical alteration, or technological augmentation, we might project our awareness across the temporal landscape. One of the most ancient and widespread approaches to this is through deep meditative or shamanic states. For millennia, various cultures have used practices like meditation, sensory deprivation, and rhythmic drumming to achieve altered states of consciousness. In these trance-like conditions, practitioners often report experiences that feel like temporal displacement, vivid, ecstatic visions of past events or future possibilities. The Australian Aboriginal concept of dream time is a powerful example where the past, present, and future are not separate but exist as a single, eternal narrative that can be accessed through ritual and ceremony. It's not about physically visiting another time, but about tuning the mind's receiver to a different frequency of reality, allowing one to witness or gather knowledge from across the timeline. These experiences are often described as feeling more real than ordinary waking life, carrying a profound sense of certainty and meaning for those who undergo them. In the modern era, this concept has found a new frontier with the use of psychedelic substances like psilocybin, LSD, and DMT. These powerful compounds can drastically alter brain function, dissolving the ego and the standard perception of a linear time. Users frequently report sensations of time dilation, where moments feel like eternities, or complete timelessness, where the concepts of past and future cease to have any meaning. Some describe archetypal visions of historical events or prophetic glimpses of things to come. While neuroscience explains these experiences as the result of a chemically disrupted default mode network, the brain system responsible for our sense of self and time, the subjective feeling for the individual is undeniably one of having journeyed beyond the confines of their personal chronology. The question becomes, is this merely a convincing neurological illusion, or could it be a glimpse into a deeper, more fluid nature of temporal reality that our normal consciousness filters out? Theories attempting to bridge this gap often draw upon ideas from quantum mechanics and higher dimensions. Some propose that consciousness isn't a product of the brain, but a fundamental property of the universe, much like mass or energy. If that's true, then a focused mind might be able to interact with the quantum field or access higher spatial dimensions where time is not a linear flow but a fixed landscape, much like the block universe we discussed earlier. In this model, advanced technology wouldn't be a time machine per se, but a consciousness amplifier or a dimensional interface that allows our awareness to navigate this landscape at will. We see this idea explored in science fiction, like in the movie Avatar, where a character's consciousness is transferred into another body, or in Altered Carbon, where human consciousness can be digitized and stored, effectively allowing a person to live across centuries. This naturally brings us to the widespread and puzzling phenomenon of precognition, the experience of knowing about a future event before it happens through means other than the five senses. History is filled with anecdotal accounts, from prophetic dreams before major disasters like the sinking of the Titanic to more personal premonitions of everyday events. The psychologist Carl Jung called this synchronicity, which he defined as meaningful coincidences that are not causally related but are connected by their significance. While mainstream science remains deeply skeptical, often attributing these experiences to coincidence, selective memory, or unconscious inference, the sheer volume of reports suggests to some that there might be more to it. Could precognition be a faint, unconscious tapping into that timeless block universe where the future is just as fixed and real as the past? It's a tantalizing idea, but one that currently resides firmly in the realm of speculation due to a lack of reproducible, controlled experimental evidence. And that is the central reason why consciousness-based time travel remains a fringe theory. For all the compelling personal testimonials, there is no reliable, scientifically validated method to induce verifiable time travel through mental means. The experiences are subjective, impossible to independently verify, and cannot be reliably replicated under controlled laboratory conditions. Without concrete evidence that can be tested, measured, and repeated, these ideas cannot graduate from fascinating philosophical conjecture to accepted scientific theory. They challenge the very framework of the scientific method, which relies on objective observation and repeatable experimentation. Yet, they persist because they speak to a deep human intuition that our consciousness is more than just a passenger in time, that it might, in ways we are only beginning to imagine, hold the key to becoming its navigator. While the idea of navigating time through consciousness remains a profound mystery, another theory offers a more concrete, though no less astounding, path to the future. This brings us to a concept that sounds like it was pulled directly from a Star Trek episode, but was in fact born from the hard mathematics of general relativity, the Alcubierre drive. Proposed by Mexican physicist Miguel Alcubierre in 1994, this theoretical engine wouldn't propel a ship through space in the conventional sense. Instead, it would manipulate the fabric of spacetime itself, effectively creating a wave that the spacecraft could surf, allowing it to achieve effective faster-than-light travel and, as a stunning consequence, journey into the future. The core principle is a breathtaking application of Einstein's equations. Alcubierre's solution involves creating a warp bubble around a spacecraft. In front of the ship, spacetime would be massively compressed, pulling the destination closer. Behind the ship, spacetime would be drastically expanded, pushing the point of origin further away. Inside this bubble, the spacecraft would reside in a flat, undisturbed patch of spacetime. It wouldn't be moving through space locally, the space around it would be moving instead. This is a crucial distinction because it sidesteps Einstein's strict speed limit. Nothing within the bubble is breaking the light-speed barrier. It's the space-time continuum itself that is contracting and expanding, and general relativity places no upper limit on how fast space-time can distort. The ship would simply be carried along by this wave, like a surfer on a tidal wave of the cosmos, potentially reaching distant stars in weeks or days instead of millennia. This method of travel has a direct and incredible implication for time dilation, which we've already established as a proven form of time travel. If a ship using an Alcubierre drive were to journey to a star 10 light-years away and return, the trip might only take a few months of ship time. But due to the relativistic nature of the journey, decades or even centuries could have passed on Earth. The crew would effectively be traveling into the future of their home planet, returning to a world that has aged far more than they have. They wouldn't be traveling backwards, but the drive would grant them a one-way ticket to the distant future, making them archaeological relics of their own era. However, the obstacles to building such an engine are, to put it mildly, astronomical. The first and most famous problem is the requirement for exotic matter. To create the warping effect, Alcubierre's equations require a form of matter with negative energy density. This isn't just an unknown material. It's a substance with truly bizarre properties, possessing negative mass and thus creating repulsive gravity or anti-gravity to push space-time apart behind the ship. While quantum mechanics allows for the existence of tiny amounts of negative energy density seen in the Casimir effect, where two uncharged plates in a vacuum are pulled together by virtual particles, the quantities needed for a macroscopic warp drive are staggering. Early calculations suggested you would need the equivalent of the mass energy of Jupiter converted entirely into this exotic material. Later refinements have brought that number down, but it remains far beyond any conceivable technology. The second major hurdle is the sheer energy requirement. Even with a more theoretically manageable amount of exotic matter, the energy needed to distort space-time on this scale is incomprehensibly vast, likely requiring the total energy output of entire stars. Furthermore, there are serious concerns about the stability of the warp bubble and the fate of anything actually inside it. Some calculations suggest that the bubble would accumulate high-energy particles as it travels, releasing them in a catastrophic burst of radiation upon arriving at its destination, potentially sterilizing the entire planet you are trying to visit. Other theorists have raised the terrifying possibility that creating a warp bubble might require a singularity, a black hole, to power it, introducing a whole new set of lethal engineering challenges. Despite these seemingly insurmountable barriers, the idea has not been abandoned. In recent years, physicists like Dr. Harold "Sonny" White at NASA Eagleworks Lab have been exploring ways to make the concept more feasible. White proposed that by altering the geometry of the warp bubble from a flat ring to a more rounded, donut-like shape, the energy requirements could be reduced from planetary scales to something more akin to the mass of a spacecraft like Voyager. While still a monumental challenge, this reframing moves the concept slightly from the realm of pure fantasy into the domain of a distant, speculative technology. Other researchers are investigating whether the intense fields generated by lasers or other devices could create microscopic warp bubbles in a lab, not to build a starship, but to test the underlying physics and see if space-time can be manipulated in this way at all. The Alcubierre drive represents a beautiful synergy between imaginative science fiction and rigorous scientific inquiry. It shows that by working within the rules of our best physical theories, we can conceive of technologies that stretch the limits of what we believe is possible. It may never become a practical reality, but its value lies in pushing our understanding of the universe. It forces us to ask deeper questions about the nature of space-time, energy, and gravity, and in doing so, it continues to inspire a new generation of scientists and engineers to dream of one day sailing the cosmic waves between the stars. Now let's dive into one of the most mystifying phenomena in all of physics, a concept so strange that Einstein himself famously called it spooky action at a distance. This is quantum entanglement, and its bizarre implications might just provide a hidden link to the nature of time itself. At its heart, entanglement is a connection between particles that is so profound and instantaneous that it seems to defy our everyday understanding of space and time. When two particles become entangled, they lose their individual identities and are described by a single quantum state. No matter how far apart you separate them, across a lab or across the galaxy, measuring the property of one particle, like its spin or polarization, instantly determines the state of its partner. This connection appears to happen faster than the speed of light, which, according to Einstein's special relativity, is the universe's ultimate speed limit for any signal or information transfer. This spooky action presents a monumental puzzle. If information isn't traveling between the particles, how do they achieve this perfect coordination? One radical possibility is that the connection between them doesn't move through space at all. Instead, it might be a fundamental link that operates outside of our conventional timeline, suggesting that cause and effect might not always follow the strict forward-facing arrow we experience. Some interpretations posit that the particles aren't communicating. They are simply revealing a deeper, underlying unity to the universe where separation is an illusion. From this perspective, the entangled pair isn't two distinct objects sending signals, but a single system that exists in a state where temporal sequence is irrelevant. The measurement here and the result there aren't a cause and an effect in the traditional sense. They are two aspects of a single, unified event that the universe registers simultaneously. This leads to a breathtaking hypothesis. Could this instantaneous link be a form of connection that transcends time, not just space? If entangled particles are truly operating outside the constraints of light speed, their correlation might be fundamentally a causal, meaning the concept of before and after doesn't apply to them. In this view, the moment of measurement on one particle and the determination of the other's state could be thought of as happening at the same time, or even with the future measurement influencing the past state without any logical paradox. This isn't about sending a message backwards in time in a way you could read. It's about the universe maintaining a consistent reality where the properties of entangled particles are correlated in a way that makes our linear perception of time seem like a local rather than a universal rule. The potential for harnessing this phenomenon for temporal communication is a dream that tantalizes physicists and futurists alike. Imagine creating a pair of entangled particles, keeping one in a secure lab and sending the other on a journey at near light speed to a distant star. Due to time dilation, the traveling particle would experience less passage of time. The idea would be to measure the traveling particle upon its arrival, which should instantly affect its twin back on Earth. But from Earth's perspective, that measurement in the future could be seen as affecting the particle in its present. While this sounds like a mechanism for sending a signal into the past, the universe has a built-in safeguard. The outcome of a quantum measurement is fundamentally random. You cannot force an entangled particle to take on a specific, predetermined state to send a message like Morse code. The instant correlation may be real, but it cannot be controlled to transmit meaningful, classical information faster than light or backwards in time. Any attempt to manipulate one particle to send a signal would break the delicate entanglement, collapsing the connection and leaving you with nothing but random noise. Despite this limitation, the door isn't completely closed. Research into quantum retrocausality explores whether the choices made in the present when measuring a particle could subtly influence the state of its entangled partner in the past. This isn't about sending a conscious message, but about the possibility that the future can exert a faint influence on the past at the quantum level to ensure a consistent outcome. Experiments like the delayed choice quantum eraser add fuel to this fire. In these setups, a decision made after a photon has been detected seems to retroactively determine how it behaved before it was detected, whether it acted like a particle or a wave. While the results remain fiercely debated and don't allow for practical time communication, they profoundly challenge our classical, rigid understanding of temporal order, suggesting that at its most fundamental level, the universe might not play by the same timekeeping rules that govern our macroscopic world. This philosophical perspective finds a powerful ally in the block universe theory we explored earlier, providing a concrete physical model for eternalism's claims. If the block universe is real, a four-dimensional structure where all of spacetime exists at once, then eternalism is simply the correct way to describe our reality. Past, present, and future are not sequential. They are just different locations within this vast, unchanging structure. Your first day of school, the moment you are experiencing right now, and your last breath are all fixed coordinates within the block, each as real and tangible as the cities of Paris, Tokyo, or New York are in space. From this vantage point, time travel isn't about rewriting history. It's simply about moving your consciousness from one temporal location to another within a reality that is complete and whole. The paradoxes that plague other theories simply melt away under eternalism's immutable logic. You cannot kill your grandfather before he sires your parent because the event of your birth is a fixed point in the block. Your attempt to do so would be just another part of the unchangeable history leading up to that event, inevitably failing or somehow ensuring the timeline remains consistent. The universe doesn't need to prevent paradoxes because in a block universe they are a logical impossibility. This stands in stark contrast to its philosophical rival, presentism. This is the view that feels most intuitive to us. Only the present moment is real. The past is gone, a collection of fading memories, and the future is not yet written, a realm of pure potential. Presentism aligns with our direct, lived experience of a flowing now that relentlessly marches forward, leaving the past behind and pulling the future into existence. It champions the idea of an open future where our free will and choices genuinely matter, carving out a new reality with every decision we make. However, presentism struggles mightily with the implications of modern physics, particularly Einstein's theory of relativity. As we discussed, relativity tells us there is no universal now. What is the present for you depends entirely on your frame of reference and motion. An event that is in the future for one observer could be in the past for another. Eternalism elegantly incorporates this reality by making all those equally valid perspectives simply different views of the same eternal block. Presentism, by insisting on a single, privileged present, finds itself at odds with one of the most well-tested theories in all of science. The implications of eternalism for concepts like morality and personal identity are nothing short of revolutionary and deeply unsettling to many. If the entire timeline is fixed, what becomes of free will? Are our choices and struggles merely illusions, just us reading lines from a cosmic script we cannot see? From the eternalist perspective, your life is not a story being written but a sculpture, already complete, with every joy and every tragedy eternally carved into its form. This can feel deeply fatalistic, diminishing the urgency of our actions and the weight of our moral responsibilities. Why strive to be better if every action is predetermined? Why fight against injustice if its occurrence is a permanent fixture of the cosmic block? Proponents argue that our experience of making choices is no less real or meaningful simply because the outcome is fixed. The feeling of deliberation, the agony of a tough decision, the joy of a hard-won victory, these are all real experiences within their respective moments in the block. The meaning is found in the experience itself, not in the illusion of authorship over the timeline. For personal identity, eternalism suggests a radical redefinition of the self. You are not just the person experiencing this single moment. You are the entire, sprawling collection of every moment of your life, from infancy to old age. All these yous exist simultaneously across the timeline. This challenges our deep-seated notion of a continuous, unitary self that persists through time. Instead, there is the you at age 5, the you at age 20, and the you at age 80, each a distinct temporal slice of a larger, four-dimensional object we call a person. A time traveler visiting their own past wouldn't be reuniting with a younger version of themselves. They would be encountering a different, earlier part of their total being. This view can be both comforting and terrifying. It means that the loved ones we have lost are not gone. They exist forever in their own time and place within the block. But it also means that our mistakes and sorrows are eternally cemented into reality, never to be erased or undone, only experienced from a different point in the timeline. Eternalism doesn't just change how we think about time travel. It demands we reconsider the very nature of our existence and our place in a cosmos of breathtaking, static grandeur. But if manipulating spacetime with a warp drive feels like engineering on a galactic scale, then our next theory suggests the universe might have already built the ultimate time machine, just waiting in the dark depths of space. Let's venture into the terrifying and awe-inspiring heart of a black hole. These cosmic monsters, formed from the collapse of massive stars, are regions where gravity is so intense that not even light can escape their grasp. But within their enigmatic boundaries, the equations of general relativity suggest something even more incredible might be possible. Due to the extreme warping of space-time, time near a black hole slows to a crawl relative to the outside universe. This is time dilation taken to its absolute extreme. An astronaut orbiting just outside the event horizon would watch their clock tick normally, but upon returning to Earth, they might find that thousands of years had passed for everyone else. They would have effectively catapulted themselves into the distant future, becoming a lone traveler from a bygone era. The real speculative leap, however, involves not just orbiting a black hole, but daring to cross its event horizon. This is where the theory becomes truly wild and fraught with peril. The primary challenge is a gruesome process known as spaghettification. As you approach a black hole, the difference in gravitational pull between your head and your feet becomes so extreme that your body would be stretched into a long, thin strand of atoms like cosmic pasta. For smaller black holes, this would happen well outside the event horizon, making entry fatal. But for a supermassive black hole, like the one at the center of our galaxy, Sagittarius A, the event horizon is so large that the tidal forces are weaker. You could theoretically cross the point of no return before being spaghettified, entering a realm where the known laws of physics break down. Now, what happens inside? This is one of the greatest mysteries in physics. Our equations point toward a singularity at the center, a point of infinite density where space and time cease to have any meaning. But many physicists believe this is a sign that general relativity is incomplete and must be united with quantum mechanics. Some theories suggest that the singularity might not be a point, but a bridge to another part of the universe or even another universe entirely, an Einstein-Rosen bridge or a wormhole. This is where the idea of a white hole enters the picture. A white hole is the hypothetical opposite of a black hole. Instead of everything falling in, everything is spewed out. It's a region of spacetime that cannot be entered from the outside, only exited. If a black hole singularity actually connects to a white hole, then falling in one end could mean being ejected from the other, potentially in a different location, a different universe, or crucially, a different time. This forms the basis of the black hole time machine theory. The intense warping of spacetime inside the black hole could twist time like curves into a loop. If you could somehow survive the journey and exit through a white hole, you might not emerge in the same moment you left. You could find yourself in the past or the future. The problem, of course, is that white holes are entirely hypothetical. No observational evidence for their existence has ever been found, and many physicists consider them to be mathematically possible but physically unlikely, as they seem to violate the second law of thermodynamics by decreasing entropy. Even if they do exist, navigating such a passage would be unimaginably chaotic. The environment inside a black hole is thought to be filled with chaotic energy, extreme radiation, and unimaginable turbulence conditions that would destroy any known form of matter. Why then do serious scientists continue to entertain such a speculative idea? It's because black holes represent the ultimate laboratory for testing our theories of physics. They are places where gravity is so strong that quantum effects must become important, forcing us to confront the need for a theory of quantum gravity. Studying these extreme scenarios, even if they seem like science fiction, helps us refine our models and ask better questions about the fundamental nature of reality. The black hole time machine theory remains one of the most fascinating thought experiments precisely because it pushes our understanding to the absolute limit, challenging us to imagine what might be possible in the most extreme corners of the cosmos. After exploring the terrifying and awe-inspiring depths of black holes, we arrive at a theory that might serve as the universe's ultimate safety mechanism, a cosmic rule that keeps those terrifying paradoxes from ever becoming a reality. This is Stephen Hawking's chronology protection conjecture. The legendary physicist, after deeply considering the implications of time travel, essentially threw up his hands and said the universe would simply not allow it. He wasn't just making a philosophical statement, he was proposing a fundamental principle of physics. Hawking suspected that any attempt to create a closed time-like curve, a path that loops back on itself in time, would inevitably trigger a catastrophic response from nature itself, a response that would destroy the time machine before it could ever be used. It's as if the fabric of reality has a built-in immune system, and time travel is the virus it is programmed to immediately seek out and eliminate. But what would this immune response actually look like? Hawking and other physicists have proposed some truly mind-bending mechanisms. One compelling idea involves quantum feedback. Imagine you're trying to create a wormhole time machine. As you pump energy into it to stabilize it, the very act of trying to open a path to the past could create a runaway feedback loop of energy. Virtual particles, those that constantly pop in and out of existence thanks to quantum fluctuations, would get caught in the time loop. With each pass through the loop, these particles would gain more and more energy, their amplitudes piling on top of each other in a destructive crescendo. The energy building up would quickly become infinite, vaporizing the wormhole in a flash of radiation long before any information or matter could pass through it. The time machine would literally be torn apart by the sheer weight of its own paradoxical potential. Another proposed guardian of chronology is the vacuum itself. The quantum vacuum is not an empty void. It's a seething, bubbling sea of energy where particle-antiparticle pairs constantly flicker into existence and then annihilate each other. Under normal circumstances, this activity is balanced and harmless, but the extreme warping of spacetime required for time travel could disrupt this delicate balance. The calculations suggest that the energy density of the vacuum could skyrocket to impossible, infinite values along the path of the closed time-like curve. This wouldn't just be a power surge, it would be a fundamental instability in the fabric of reality. Spacetime itself would become so stressed that it would rather break, collapsing into a singularity or simply refusing to form the path than allow a paradox to occur. The universe, in its own inscrutable way, seems to choose consistency over convenience. This leads us to the core philosophical question behind Hawking's conjecture. Why would the laws of physics be so adamantly opposed to time travel? The answer likely lies in the concept of causality, the principle that cause must precede effect. This isn't just a rule we invented, it appears to be a foundational pillar upon which our entire universe is built. Our ability to make predictions, to understand the world through science, and to have a coherent experience of reality all depend on the unwavering arrow of causality. If that arrow could be twisted into a loop, the entire logical framework of the universe would fall apart. Physics, as we know it, would cease to function. Hawking's conjecture is essentially nature's way of preserving its own logical integrity. It posits that the universe has a profound, fundamental aversion to paradoxes, not out of malice, but out of a necessity to remain logically consistent and predictable. It ensures that the universe continues to make sense, from the largest galaxy to the smallest subatomic particle, by forbidding the one thing that could unravel it all. But if navigating the lethal gravity of black holes or stabilizing a warp bubble with exotic matter seems impossibly far off, there is another path to the past and future that feels increasingly plausible, even if it redefines the very meaning of travel itself. This is the concept of digital time travel. Forget about chrome-plated machines. Imagine instead that the vessel is your own mind. The idea is to create a perfect digital copy of your consciousness, your memories, your personality, your very sense of self, and upload it into a sophisticated virtual reality simulation of a different era. You could walk through ancient Rome, witness the signing of the Declaration of Independence, or visit a cityscape 500 years from now, all from the safety of a pod, experiencing it as vividly as you are experiencing this moment right now. The technological path to such an achievement is as daunting as it is fascinating. It rests on two monumental pillars: whole brain emulation and historical simulation. The first requires scanning a human brain in unimaginable detail, mapping the precise structure and connection of all 86 billion neurons and their trillions of synapses. We are talking about a resolution far beyond today's MRI machines, likely requiring advanced nanotechnology to scan a preserved brain layer by intricate layer. Then we would need to accurately simulate the electrochemical behavior of this neural network in a computer of immense power, one capable of running a model as complex as a human mind. The second pillar is just as challenging, building a perfect dynamic simulation of a historical period. This wouldn't be like a video game level. It would need to be a living, breathing digital world populated by incredibly sophisticated artificial intelligences that behave exactly like people from that era would, with their own desires, knowledge, and flaws. Every dusty road, every changing weather pattern, every whispered conversation in a tavern would have to be rendered and accounted for to create a truly immersive and authentic experience. We are generations, perhaps centuries, away from such technology, but it doesn't violate any known laws of physics. It is, in many ways, an engineering problem rather than a physics problem. This leads us directly into a philosophical quagmire that is every bit as deep as any grandfather paradox. If you upload your consciousness into a simulation of 1920, are you actually time traveling? Or are you just an incredibly sophisticated tourist in a very convincing theme park? The you having the experience is just a copy, a pattern of information running on a computer. The original, biological you is still sitting in the pod in the 21st century. This raises profound questions about identity and consciousness. Is that digital copy truly you, or is it just a duplicate that believes it is you? If the simulation allows you to feel the virtual sun on your face and the thrill of being in the past, does the distinction even matter for the quality of the experience? This concept, explored in films like The Matrix and Source Code, forces us to ask what truly constitutes reality. If the simulation is perfect and your conscious experience within it is indistinguishable from genuine time travel, then in a very real sense, for the mind having the experience, it is real. This form of time travel offers a tantalizing solution to the most frustrating paradoxes. Since you're not physically present in the past, you cannot accidentally step on a butterfly and alter the course of history. You are merely an observer in a pre-recorded or perhaps dynamically generated reconstruction. There is no risk of a grandfather paradox because your digital self cannot interact with the actual historical world. It can only interact with a flawless copy of it. This makes digital time travel arguably the safest and most ethically manageable form of temporal exploration. You could satisfy your curiosity about history without the terrifying responsibility of potentially erasing your own future. Yet this safety comes with its own eerie and potentially dystopian implications. Who controls these historical simulations? Would they be accurate recreations or would they be sanitized, propaganda-filled versions of the past designed to push a certain narrative? If you can simulate the past, what's to stop someone from simulating a future? This could lead to a society that retreats into idealized or exciting virtual realities, neglecting the actual world around them. Furthermore, the very act of creating a perfect copy of a human consciousness introduces a terrifying possibility: digital slavery. If a copy of you can be created, it could potentially be forced to relive the same traumatic historical event over and over for research or even entertainment purposes. Would that copy have rights? Is it a person or just a piece of software? Digital time travel may avoid the paradoxes of physics, but it opens a Pandora's box of ethical and existential questions that challenge our understanding of what it means to be human, to have free will, and to experience a life that is authentically our own. It presents a future where the past is not a place we visit, but a product we consume. This brings us to a truly cosmic solution to the time travel puzzle, one that reimagines the entire multiverse as a vast library of moments, each waiting to be visited. Imagine not a single timeline, but an infinite array of parallel universes, each one a unique iteration of reality. Now, imagine that these universes aren't just different because of choices made, but because they exist at different points along a universal clock. In this staggering model, time travel wouldn't mean moving along your own past. It would mean hopping from your current universe to another one that is a perfect replica of your world, but at an earlier or later date. You wouldn't be rewriting history. You'd simply be changing your address in the cosmic archive, stepping into a reality where the year is 1920 or 3000, leaving your original universe completely untouched and unchanged. This multiverse theory of time travel is fundamentally different from the many worlds interpretation we discussed earlier. Many worlds is about branching. A new universe splits off from the original every time a quantum event occurs, creating a tree-like structure of possibilities. In this new model, the universes don't necessarily branch from each other. They may have always existed in a static, infinite ensemble. Think of it like a film archive. Many worlds is like a single film strip that keeps duplicating itself at every frame, creating endless alternate versions of the story. This multiverse model is more like a vault containing every single frame of the film, each one existing independently and simultaneously. Time isn't a river flowing in one direction. It's a dimension of the multiverse itself, much like space. A time traveler, in this view, is just a multidimensional tourist moving from the universe labeled 2024 to the one labeled 1920. The most elegant feature of this theory is its effortless resolution of every single time travel paradox. The grandfather paradox simply cannot happen. If you journey to a universe where your grandfather is young, and for some reason you prevent him from meeting your grandmother, you haven't erased yourself. You've just created a new timeline within that universe where you were never born. But your original self from your original universe remains perfectly intact and unaware. You are a visitor, an anomaly in this new world, and your actions only affect the future of this new reality, not your own past. There is no logical contradiction because you are not altering a fixed history. You are interacting with a different parallel history. The bootstrap paradox also vanishes, as any object or information you bring with you wasn't created in this new universe's past. It was imported from an entirely separate cosmos. It has a point of origin, it came from you. However, this introduces a profound and somewhat unsettling question about personal identity. If you leave your universe behind and take up residence in another, are you still you? In a sense, yes, you have all your memories and your continuous consciousness, but the people you meet in this new old world, while identical to those you knew, are not the same individuals. They have their own histories and their own futures that are now separate from the ones you remember. The parents you might visit in this past are not your actual parents. They are perfect duplicates from a different reality. You would be a stranger to them, a person with no history in their world, which could lead to a deep sense of existential isolation. You could observe, but you could never truly participate in a way that feels authentic, because your very presence is an impossibility in that universe's otherwise consistent history. This model also raises fascinating practical questions. How would you even navigate such an infinite multiverse? How would you find the specific universe that corresponds to, say, London on April 15, 1912? You would need a technology capable of not just moving through space, but of scanning, identifying, and then connecting to a specific point in the cosmic spectrum of all possible realities. The energy and precision required are unimaginable. Furthermore, once you arrived, how would you return? Your original universe would be just one in an infinite sea, a needle in a haystack of cosmic proportions. A one-way trip would be the most likely outcome, stranding you forever in a reality that is almost yours but forever out of reach. This form of time travel offers unparalleled freedom from paradox, but it comes at the cost of ultimate exile, transforming the traveler into a permanent ghost in someone else's machine, forever separated from the world that truly made them. What if the most accessible time machine wasn't a piece of technology, but something we all possess and use every single night? This brings us to a theory that lives at the fascinating intersection of neuroscience, psychology, and pure metaphysics: the idea that we might be time traveling through our dreams. For centuries, cultures around the world have imbued dreams with profound significance, often viewing them as portals to other realms or messages from the past and future. In ancient Greece, dreams were considered direct communications from the gods, offering prophecies and guidance. Indigenous cultures frequently incorporate dream interpretation into their spiritual practices, believing that during sleep, the soul can journey to visit ancestors or see events in distant times. This historical context shows a deep, persistent human intuition that the dreaming mind might have a unique relationship with time, one that operates outside the rigid constraints of our waking reality. The modern iteration of this idea often centers on the phenomenon of precognitive or prophetic dreams, those startlingly vivid dreams that seem to depict a future event with uncanny accuracy. Many people report dreaming of a specific, mundane detail, like a broken clock or a forgotten conversation, only to encounter that exact scenario days or weeks later. The psychological explanation for this is often rooted in the concepts of coincidence and selective memory. Our brains are pattern recognition machines, and we naturally remember the one dream that seemingly came true while forgetting the thousands that did not. This is known as confirmation bias. Furthermore, our subconscious mind is constantly processing vast amounts of information below the level of our awareness. A precognitive dream might simply be our brain making a sophisticated prediction based on subtle cues we've registered but not consciously acknowledged, then presenting it to us in a dramatic, symbolic narrative during sleep. For those seeking a more active form of temporal exploration, lucid dreaming offers a tantalizing possibility. A lucid dream is one in which you become aware that you are dreaming, often gaining the ability to control the dream's narrative, environment, and characters. Proponents of dream-based time travel suggest that a highly skilled lucid dreamer could, in theory, consciously choose to visit a different time period, They could will the dreamscape to transform into Victorian London or a far future cityscape, interacting with the environment and even conversing with dream characters that represent historical figures. The experience subjectively could feel incredibly real and immersive. From this perspective, the mind becomes the time machine and the dream world is the simulation, a personally generated reality that can be programmed to resemble any era imaginable. However, this is where the theory firmly steps from the plausible into the metaphysical. While the experience of visiting the past in a lucid dream is undeniably powerful for the individual, there is a critical distinction to be made. Is it time travel or is it time tourism? The dream version of ancient Rome is not the actual past. It is a reconstruction built by your own brain from everything you have ever read, seen, or imagined about ancient Rome. It's a breathtakingly detailed and immersive historical reenactment, but it is ultimately a fantasy built from information you already possess, combined with your brain's incredible capacity for creative filling in. You cannot learn new, verifiable historical facts this way that you didn't already know subconsciously. If you discover something in the dream, it's because your mind already contained the pieces and assembled them in a novel way. This is the fundamental reason why dream time travel remains outside the boundaries of mainstream science. Science relies on objectivity, verification, and repeatability. A personal, subjective dream experience cannot be independently verified or tested. If one person dreams of a historical event with perfect accuracy, it could be dismissed as incredible luck or prior knowledge. For it to be scientifically validated, we would need a way to record dreams objectively, compare them to a known historical record, and demonstrate that the dreamer accessed information they could not possibly have known through any conventional means. We have no technology or methodology that can accomplish this. Therefore, while dreams may be a fascinating window into the subconscious and a powerful tool for creativity and introspection, they currently offer no empirical evidence for functioning as a genuine conduit through time. They remain one of the most beautiful and mysterious aspects of the human experience, a personal cinema where the boundaries of time and self become wonderfully and perhaps deceptively fluid. But if the multiverse offers an infinite array of destinations and dreams provide a personal simulation, the ontological paradox presents a puzzle that strikes at the very heart of existence and origin. This mind-bending concept, sometimes called the self-created object paradox, describes a situation where an object, a piece of information, or even a person exists without any discernible point of creation. It is caught in a closed, timeless loop, seemingly creating itself from nothing. We touched on this earlier with the idea of giving Shakespeare his own plays, but it becomes even more personal and unsettling when applied to the very origin of a human being. Imagine a scenario where a time traveler journeys to the distant past and through a series of events becomes their own direct ancestor. Perhaps they assume a new identity, settle down, and start a family line that eventually leads to their own birth centuries later. This creates a baffling circularity of cause and effect. Where did this person originally come from? Their entire genetic lineage, their very DNA, can be traced back to their own actions in the past. They are their own creator and their own creation, a closed loop with no beginning. There is no initial cause that started the cycle. The timeline simply folds in on itself, presenting a consistent and stable reality that nonetheless defies our fundamental understanding that everything must have an origin. This paradox forces us to confront deep philosophical questions about existence and identity. If you are your own ancestor, does your life have any independent meaning, or are you merely a necessary step in a predetermined cycle? Your entire existence is both the cause and the effect, which can feel incredibly deterministic, robbing life of any sense of free will or novelty. You are not a unique event in the universe. You are a fixed point in a loop, destined to play out the same role again and again. It challenges the very notion of a soul or a unique self, suggesting that identity might just be a pattern that can be infinitely recycled within the timeline with no true starting point. This chilling idea has been masterfully explored in science fiction, most notably in the iconic film The Terminator. The core plot is a perfect example of an ontological paradox. In the original film, the Resistance fighter Kyle Reese is sent back in time to protect Sarah Connor from a killer android, the T-800. He succeeds, and in the process, he fathers a child with Sarah John Connor, the future leader of the human resistance. Later films reveal that the advanced technology for the Skynet AI, which eventually wages war on humanity, was reverse-engineered from the damaged CPU of the very same T-800 that was sent back to kill Sarah. So, without Skynet sending the Terminator back, John Connor would never have been born to lead the fight against them. And without the remnants of that Terminator, Skynet itself would never have been created. Both the hero and the villain, the savior and the destroyer, are locked in a cycle where each is the cause of the other's existence. The timeline has no original, unaltered state. It is entirely self-contained and self-referential. What makes the ontological paradox so stable and therefore so fascinating is that it doesn't create a logical contradiction like the grandfather paradox. There is no moment where you are erased from existence. The timeline is perfectly consistent, it's just that the chain of causality forms a circle rather than a line. From a physics perspective, this is a much more tenable form of time travel. The universe doesn't need to prevent it because it doesn't break any rules. It merely presents a history that has always included the time traveler's meddling. The paradox is not in the physics but in the philosophy. It confronts us with the possibility that our entire reality and our place within it might be one giant, inexplicable loop where the question, where did it all begin, has no answer because there was no beginning, only an eternal repeating now. But what if the ultimate key to time travel isn't a massive cosmic structure or a quantum phenomenon, but a single, elusive particle? This brings us to a concept that has captivated physicists and science fiction writers for decades, the tachyon. In the 1960s, physicists analyzing Einstein's equations made a startling theoretical discovery. The famous formula E equals mc squared dictates that any particle with mass must travel slower than the speed of light. But what if a particle always traveled faster than light? The math suggested something incredible. Such a particle would be forced to travel backwards in time. This hypothetical faster-than-light particle was dubbed the tachyon from the Greek word tachys, meaning swift. To understand why a tachyon would behave this way, we need to look at the bizarre implications of Einstein's relativity. As a normal object with mass accelerates towards the speed of light, its energy requirements become infinite, an impossible barrier. For a tachyon, this light-speed barrier works in reverse. It's theorized to always travel faster than light, and if it somehow lost energy, it would accelerate, approaching infinite speed as its energy dropped to zero. But the real mind-bender is its relationship with time. According to the equations of special relativity, as an object's velocity approaches the speed of light, time dilation becomes extreme. For a photon of light itself, time does not pass at all. For a tachyon moving faster than light, the equations produce a solution where its proper time becomes an imaginary number, a mathematical concept that, when interpreted, suggests the particle is traveling backwards along the timeline. From our perspective, a tachyon emitted from a source in our future could be detected by an observer in our past. This leads directly to the most significant problem with tachyons, their potential to violate causality, the fundamental principle that cause must precede effect. Imagine a simple experiment. You build a tachyon transmitter and receiver. You decide that if you receive a tachyon signal at noon, you will immediately send one back. Now, because these particles move backwards in time, the signal you send at noon could arrive at the transmitter at 11:59 in the morning. This means the response arrives before the original signal was even sent. An observer at the transmitter could then receive the response and use that information to decide not to send the original signal at noon. You've created a paradox where the effect prevents its own cause from ever happening. This is a direct assault on the logical foundation of the universe, making events completely unpredictable and physics as we know it impossible. For this primary reason, most physicists are deeply skeptical that tachyons exist as real, detectable particles. The universe appears to have a profound aversion to paradoxes, as Stephen Hawking's chronology protection conjecture suggests. If tachyons did exist and could be controlled, they would rip causality to shreds. Some theories propose that tachyons could exist but be impossible to detect or interact with in a meaningful way, perhaps only influencing the universe on a grand scale. Others suggest they might have played a role in the rapid inflation of the universe right after the Big Bang, a period when spacetime itself expanded faster than the speed of light. But as a tool for building a time machine, they present insurmountable logical problems. They are less a practical proposal and more a fascinating what-if that helps us test the boundaries and consistency of our physical theories. Despite their dubious physical reality, tachyons have achieved immortality in the realm of science fiction, where their time-bending properties make for fantastic storytelling. They are the go-to technobabble explanation for everything from faster-than-light communication to time travel itself. The word itself just sounds futuristic and powerful. In countless novels, movies, and TV shows, tachyon beams or tachyon fields are used to detect cloaked ships, power incredible engines, or inadvertently open portals to the past. Their use in fiction often glosses over the pesky causality problems, focusing instead on the sense of wonder and possibility they represent. They are a narrative shorthand for cutting-edge, almost magical technology that operates by rules we don't yet understand, allowing writers to explore the thrilling and terrifying consequences of meddling with time without getting bogged down in complex physics. This enduring popularity is a testament to the power of a compelling scientific idea, even one that remains forever out of reach in the real world. This brings us to one of the most profound and personal questions at the heart of our journey. If time travel were possible, what would it mean for our free will? Does the ability to visit the past or future imply that we are the ultimate authors of our destiny? Or would it reveal that our choices are nothing but an illusion, and that every event is locked in an unchangeable script? This conflict strikes at the very core of our understanding of self, agency, and our place in the cosmos. Consider the two dominant models we've explored. The Novikov self-consistency principle and the block universe theory present a reality of profound determinism. In this view, the entire timeline is fixed and immutable. If you traveled to the past, you were always there. Your every action was a predetermined part of history. This means that even with a time machine, you possess no real power to change anything. Your feeling of making a choice to save a life or prevent a disaster is just that, a feeling. The outcome was sealed billions of years ago. You are not a pilot steering the ship of time. You are a passenger on a train with a single, unalterable destination, reading from a script you had no hand in writing. This is a universe without free will in the libertarian sense, where our deepest struggles and triumphs are rendered as pre-recorded events in a cosmic film, leaving no room for genuine alternative possibilities. On the opposite end of the spectrum, the many worlds interpretation seems to offer a thrilling liberation for the will. Every decision spawns a new universe. If you travel back and alter an event, you don't rewrite history. You simply step into a new branch where that event unfolded differently. In this infinite multiverse, every possible choice is made somewhere. This model appears to maximize free will. Your choices genuinely matter because they create entirely new realities. You have the power to become a version of yourself who is an astronaut, a baker, or a time-traveling hero simply by making a decision. Yet this leads to a different philosophical quandary. If every possible you makes every possible choice, are you truly choosing? Or are you just experiencing one predetermined path out of an infinite number? Your choice in one universe is mirrored by a different choice in another, which can make your personal sense of agency feel diluted across the multiverse, like a single voice in an infinite choir. Between these two extremes lies a compelling middle ground known as compatibilism. This philosophy argues that free will and determinism are not mutually exclusive. Compatibilists redefine free will not as the ability to do otherwise in an absolute sense, but as the ability to act according to one's own desires, motivations, and reasons without external coercion. You could still have free will in a deterministic universe if your actions flow from your own character and beliefs. In a Novikov-style timeline, your journey to the past and your actions there are indeed predetermined, but they are predetermined because of who you are. Your personality, your values, your fears, these are what cause you to act in a way that is consistent with the timeline. Your will is not free to break the laws of physics or create paradoxes, but it is free in the sense that it is an authentic expression of your own internal state. You are still the author of your actions, even if the story has already been written. Ultimately, the different models of time travel serve as powerful lenses through which to examine our own human condition. We live our lives forward, gripped by the powerful intuition that our choices matter and that the future is unwritten. We feel the weight of responsibility for our actions. Yet, in hindsight, our personal histories often feel inevitable, as if every decision led inexorably to this precise moment. Time travel theories magnify this tension to a cosmic scale. They force us to ask whether we are tiny gods sculpting our reality with every thought, or intricate clockwork mechanisms playing out a beautiful, predetermined design. The answer may lie beyond our current grasp, but the question itself is a vital part of what makes us human. Our relentless desire to understand not just the universe, but our own role within it. Whether we are prisoners of time or its masters, the journey of discovery continues to define us. Long before Einstein penned his equations or science fiction writers dreamed of time machines, humanity was already weaving tales of temporal transcendence into the very fabric of its myths and spiritual beliefs. This deep-seated fascination suggests that the desire to step outside the linear flow of time is not just a scientific curiosity, but a fundamental part of the human psyche. Across countless cultures and millennia, stories have emerged that feature concepts strikingly similar to our modern ideas of time dilation, temporal loops, and journeys to otherworldly realms where the normal rules of time do not apply. Consider one of the most ancient and vivid examples found within Hindu scripture. The epic Mahabharata tells the story of King Kakadmi and his daughter Revati, who journey to the heavens to meet the creator god Brahma. Their audience is brief, but when they return to Earth, they are shocked to discover that eons have passed. What felt like mere moments in the celestial realm amounted to thousands of years on their home planet. This is a breathtakingly precise allegory for the relativistic time dilation we understand today, a narrative born thousands of years ago that perfectly captures the essence of how gravity and velocity can stretch and compress time itself. This theme of a single moment expanding into vast stretches of time is a recurring motif in global folklore. The classic Japanese tale of Urashima Taro mirrors this concept. A fisherman rescues a turtle and is rewarded with a visit to the magical undersea palace of the dragon god Ryujin. He spends what feels like a few days in this blissful realm, but upon returning to his village, he finds that 300 years have flown by. The story poignantly ends with him opening a forbidden box, releasing a cloud of smoke that instantly ages him to dust, a powerful metaphor for the irreversible and often tragic nature of time's passage, and a warning about the perils of trying to reclaim a lost past. Similarly, Irish mythology is rich with stories of mortals venturing into the Shia mounds, the homes of the fairy folk. These encounters often end with the human emerging to find that a night of feasting and music in the magical realm was centuries in the human world, leaving them estranged from everything and everyone they once knew. Perhaps the most profound and complex concept is the Australian Aboriginal understanding of dream time, or Jukurpa. This is not a myth in the Western sense of a fictional story, but a foundational spiritual belief system. Dreamtime refers to the sacred era of creation, but it is not a past event that is over and done with. It is a continuous, eternal reality that exists parallel to our everyday waking life. Through ritual, ceremony, song, and art, Aboriginal people are believed to be able to connect with this everlasting dreamtime. It is a state of being where past, present, and future are interconnected and accessible. This isn't about building a machine to travel to 1920. It's about using cultural knowledge and spiritual practice to tap into a timeless dimension where the ancestors and the creation stories are perpetually alive and present. This represents a form of cultural time travel that is woven into the very identity and continuity of the world's oldest living culture. So why does this theme appear so universally? The reasons are as deep and varied as the human experience itself. On one level, these stories function as a psychological coping mechanism for our mortality. The awareness of our own inevitable end is a uniquely human burden. Myths that allow for travel outside of linear time offer a narrative solace, a fantasy of escape from the one fate that none of us can avoid. They allow us to imagine a world where we could correct past mistakes, witness historical wonders, or simply have more time. These tales also served an important pedagogical purpose long before the scientific method was formalized. They were a way to explore and explain the perplexing nature of time itself, why some moments seem to fly while others drag, why the past feels so distant yet can be recalled in an instant, and why the future is forever unknown. They were ancient thought experiments using narrative to grapple with questions that physics would only later approach with mathematics. Furthermore, they often carried moral weight. Stories like that of Urashima Taro are clear cautionary tales, warning against the dangers of curiosity, the disrespect of divine gifts, or the simple, heartbreaking truth that you can never truly go home again. This enduring cross-cultural obsession reveals something essential about us. The concept of linear, irreversible time often feels like a prison. From the moment we gain consciousness of yesterday and tomorrow, we yearn for the key. Whether through the sacred rituals of dream time, the epic journeys of ancient kings to the heavens, or the quantum equations of a modern physicist, humanity's quest to transcend the temporal is at its heart a quest for meaning, for mastery over our fate, and for a deeper connection to the universe that ultimately binds all moments into one. Now, if the idea of a timeless universe or a multiverse of moments has you questioning the very fabric of reality, wait until we explore a theory that comes from one of the most promising frontiers of modern physics itself. This is the world of loop quantum gravity, a bold and sophisticated competitor to string theory in the quest to unite general relativity with quantum mechanics. And within its complex mathematics lies a startling possibility, a new path to time travel that doesn't require the terrifying singularities of black holes. To understand why this is such a big deal, we need to recall the classic problem with black hole time machines. General relativity tells us that at the heart of a black hole lies a singularity, a point of infinite density where the laws of physics break down completely. It's this singularity that creates the closed time-like curves that could, in theory, allow for time travel. But infinities in physics are usually a sign that our theory is incomplete, that we're missing a crucial piece of the puzzle. Loop quantum gravity, or LQG, aims to provide that missing piece by reimagining the very structure of spacetime. Instead of treating space as a smooth, continuous backdrop, as Einstein did, LQG proposes that space is actually granular. It's composed of tiny, indivisible loops or quanta of space, a fabric woven from a billion tiny threads. This granularity has a profound consequence. It prevents matter from collapsing into an infinitely dense point. This is where the magic happens for time travel. In the LQG model, the gravitational collapse of a star doesn't end in a singularity. Instead, the immense pressure and density cause a quantum repulsion effect, a kind of quantum bounce. This bounce could transform the black hole into a white hole, a region of spacetime that cannot be entered from the outside, but which explosively expels all the matter and energy that originally fell in. But here's the incredible part. Some solutions within LQG suggest that this transition from black hole to white hole could create a stable, traversable tunnel through spacetime, a wormhole without a singularity at its center. Without that destructive, infinite point, the closed time-like curves that form within this tunnel could, in theory, be navigable. A traveler could pass through this quantum-corrected wormhole and emerge not only in a different place, but in a different time, all without being spaghettified or crushed into oblivion. This approach stands in stark contrast to how string theory, the other great candidate for a theory of everything, handles the problem. String theory operates in a smooth, continuous spacetime with extra, curled-up dimensions. To resolve the singularity and enable time travel, string theory often relies on complex configurations of these higher dimensions and exotic objects called branes. The focus is on finding a special, stable solution within a vast landscape of possibilities. Loop quantum gravity, on the other hand, makes a direct prediction from its core principles that the singularity cannot exist due to the discrete nature of space itself. The removal of the singularity isn't a feature to be discovered in a specific model. It's a fundamental outcome of the theory's basic architecture. This gives LQG's proposal for time travel a certain elegance and inevitability that many physicists find compelling. Recent research has pushed these ideas from pure speculation into the realm of tangible, albeit highly theoretical, models. Physicists like Carlo Rovelli and others have published papers exploring these quantum-extended spacetime geometries. They use sophisticated mathematics to show how the quantum bounce creates a bridge, a Planck star core inside what we would perceive as a black hole, that connects to another region of the universe or another time. The calculations indicate that while the journey through such a tunnel would still be incredibly rapid from the traveler's perspective, the exit could be into a future or past that is vastly different from their point of origin. The models are still in their infancy and face significant challenges, particularly in describing the exact conditions a human would experience. However, they represent a monumental shift. They move the conversation from time travel is impossible because of singularities to time travel might be possible if we can harness the quantum nature of gravity. This opens up a new, exhilarating frontier in theoretical physics, suggesting that the key to unlocking the secrets of time might not lie in the immense but in the infinitesimally small. But if navigating the quantum-corrected tunnels of loop quantum gravity feels like a distant dream, we are ultimately left with the most immediate and human question of all. Just because we could travel through time, should we? This final theory isn't about physics or mechanics. It's a deep dive into the profound ethical chasm that would open beneath our feet the moment a working time machine became a reality. The power to alter the past is the ultimate form of power, and with it comes a responsibility so immense it could crush the human spirit. The most immediate moral dilemma is the simplest to state and the most complex to resolve. Do we have the right to change history? On the surface, the answer seems obvious. Who wouldn't want to prevent atrocities like the Holocaust, stop a pandemic at its source, or avert a catastrophic war? This is the fix-it fantasy, the dream of being a benevolent God who heals the wounds of history. But this impulse is dangerously naive. History is an impossibly complex and interconnected web. The assassination of a single archduke in Sarajevo sparked a global war that redrew the map of the world. An unknown artist's rejection from art school in Vienna set in motion a chain of events that led to the deaths of millions. We have no way of predicting the second and third order consequences of even the smallest change. Preventing a tragedy in one time and place might inadvertently erase a future medical breakthrough born from the desperation of that era, or eliminate the very social movements that emerged to prevent such horrors from happening again. The well-intentioned time traveler could become the greatest mass murderer in history, wiping out billions of people whose existence was contingent on that original, unaltered timeline, all in the name of saving a few million. This is the ethical equivalent of performing brain surgery with a wrecking ball. This leads directly to the crushing weight of what philosophers call the responsibility of knowledge. A time traveler would possess foreknowledge of events, making them an omniscient observer burdened with the terrible duty to act. But acting on that knowledge is what creates paradoxes. If you know a disaster is coming, your very attempt to stop it could be the cause. This is the predestination paradox we explored earlier, but viewed through an ethical lens. It transforms the traveler from a potential savior into a predetermined agent of fate, robbing them of any moral agency. Their choice is an illusion, and they are condemned to play their part in a tragedy they saw coming. Even in a many-worlds model where you simply jump to a new branch, you are still making a choice to abandon one universe to its fate while you escape to a better one. This isn't heroism, it's the ultimate form of abandonment. The ethical burden isn't lessened, it's multiplied across infinite realities. Science fiction has long served as our laboratory for exploring these terrifying dilemmas. Ray Bradbury's classic short story, A Sound of Thunder, is the quintessential tale of unintended consequences. A time tourist on a prehistoric safari steps off the designated path and crushes a single butterfly. This tiny action ripples forward through millennia, altering the very fabric of language and society in his own time. The story is a perfect allegory for the fragility of history and the arrogance of believing we can meddle with forces we cannot possibly comprehend. On a grander scale, stories like Stephen King's 11/22/63 grapple with the personal cost and the unforeseen domino effects of changing a major historical event. The protagonist discovers that preventing the assassination of JFK leads to a dystopian future far worse than the one he knew, forcing him to undo his own work and allow the tragedy to happen. These narratives aren't just entertainment, they are vital thought experiments that force us to confront the price of playing God. Ultimately, the greatest ethical imperative might be one of restraint. The most moral use of a time machine could be to never use it at all for intervention, to treat the past as a museum we can observe but must never touch. This philosophy of non-interference is a central pillar in many time travel stories, from the Prime Directive in Star Trek to the strict protocols of time agencies in other tales. It acknowledges that our understanding is limited, our motives are often selfish, and the risk of catastrophic failure is too high. The true test of our species might not be whether we can build a time machine, but whether we are wise enough to leave it turned off. The power to change time is the ultimate temptation, and resisting it may be the highest ethical achievement humanity could ever reach. And so we find ourselves at the end of our journey through the looking glass, having explored 30 different windows into one of the most captivating ideas humanity has ever conceived. We've ventured from the solid, proven ground of Einstein's time dilation to the wild, speculative shores of cosmic strings and quantum bubbles. We've seen how black holes might hide tunnels to other eras, how the entire universe might be a single, frozen block of spacetime, and how our own consciousness might be the only vessel we need to sail the rivers of time. What's truly astonishing is the sheer range of these theories. On one end, we have the hard, mathematical certainty of general relativity, which tells us that jumping forward in time is not just possible but happening all around us, verified by the satellites in our sky. On the other end, we have the philosophical and metaphysical, From the Novikov principle's assertion of a fixed fate to the mind-bending possibility that time itself is nothing but a persistent illusion. This spectrum, from laboratory-verified science to the farthest reaches of theoretical imagination, shows that time travel isn't a single question, but a whole universe of questions about the nature of reality itself. So why does this concept hold such an unshakable grip on us? Perhaps it's because time is the one prison we all inhabit. We are born, we live, and we die, forever carried forward on a current we cannot stop or reverse. Time travel represents the ultimate freedom from that prison. It's the dream of a second chance, the desire to witness history firsthand, the curiosity about what lies ahead, and the profound hope that our stories might not be finite. It allows us to play out our greatest hopes and our deepest fears in a safe space, whether that's in the equations of a physicist, the pages of a novel, or the frames of a film. It is, at its heart, a conversation about what it means to be human in a universe of immense and mysterious scale. Now, we want to hear from you. With 30 theories laid out, which one captures your imagination the most? Does the paradoxical elegance of a predestination loop intrigue you, or does the liberating infinity of the multiverse feel more like home? Are you a fan of the hard physics behind wormholes, or does the philosophical punch of a timeless universe really make you think? Let us know your favorite in the comments below. We absolutely love reading these discussions and seeing which ideas spark your curiosity. If this journey through the mysteries of time has left you hungry for more, you're in the right place. We're dedicated to exploring the universe's biggest questions, from the secrets of black holes to the puzzles of quantum mechanics. Make sure to subscribe and hit that notification bell so you don't miss our next adventure into the unknown. Thank you so much for joining us on this incredible ride. Keep wondering, keep questioning, and never stop looking up.